Okay, I would like to thank the organizer for inviting me. It's a very nice conference. I enjoyed very much so far. So what I'm going to talk about today is fast network community detection by a new method we call SCORE. So this is in collaboration with my former student, Pengsheng Ji, who is right now at the University of Georgia. So recently, there's a lot of interest in social network. And okay, I think one of the reasons is because of the emergence of the online network community, such as LinkedIn, Google Plus, and Facebook, and so on and so forth. So there's a certain ambition that by understanding the social network, people can improve many aspects of our lives and science. Okay. What I'm going to talk about today is a specific problem which has received a lot of interest in social network, so-called community detection problem. In statistics, we usually call it clustering problem. Okay, I think they're the same problem. I'm going to consider idealized setting, but this can be easily generalized, more complicated setting you would be interested in. I would start with undirected network. Later, I'm going to talk about the direct network. Okay. The data you can think about is unweighted network. It's basically matrix 0 and 1. So the data is a JSON matrix n by n, n is the number of nodes. When we have 1, it means the load I and the load j is collected. Otherwise, it's 0. We assume that it's k, which is relatively small number, like 2 or 5, k perceivable communities, so that the set of all nodes can be split into disjoint subsets. Okay, you can have overlapping, you can generate overlapping community, but okay, here's my assumption so far. Now, for each node, it can belong to either of these k subset. Okay, the main problem is given a node to predict which community it belongs to, or to predict community label. Okay, so this is well-defined community detection problem or the clustering problem. Okay. I would like to visualize this as a statistician. I would like to visualize a JSON matrix as 2 parts, signal part and noise part. Okay. For all the ones in the matrix, I visualize them as a Bernoulli random variable. So therefore, the Bernoulli random variable, I assume they are independent of each other, and this is the probability of the Bernoulli random variable equals to 1. Okay. So this is the expectation of this matrix. I call it the signal, and the remainder part I call it noise. Okay. So in this very simple setting, the noise matrix is very simple. It's called the generalized Wigler matrix in the recent literature of random matrix theory. It's symmetrical and it's zeros on the diagonal. Here, for simplicity, I do not consider a node is collected to itself. So on the diagonal, it's always 0. Okay. Then the upper triangle are independent centered Bernoulli. When I call centered Bernoulli, you basically just take the Bernoulli, which takes values 0 and 1, subtract by the mean. Okay. Now the question is how to estimate this EX matrix. Okay. Because this diagonal is 0, it's more convenient to write it as any arbitrary matrix subtracts diagonal. So this is equivalent to how to estimate this omega. Obviously, the community structure is contained in this matrix or this matrix. So how to estimate it? This problem is challenging for the following reasons. First of all, this matrix X is very sparse in the sense that every row has relatively few ones. So if you have n node, in many social networks, they are only like 10 times n or 20 times n ones in the whole matrix. So, and this matrix of interest is n by n, so it has capital O n squared, that many parameters. If you use this many 10 times n data to estimate n by n matrix, that's very challenging. And our approach is to exploit the structure of the community structure to impose a low rank assumptions on this omega. Okay. Okay, is this understandable? Okay. We're going to impose a low rank structure on omega, and that makes this problem solvable. Okay. What? What? Omega, okay. So omega is okay because this matrix is the Bernoulli probability matrix. Okay. By the assumption the diagonals are 0. So I'm going to, okay, so this matrix can be sort of any matrix subtracted by the diagonal. Okay, so in order to model this is equivalent to model omega. And I'm going to model omega directly. Does that make sense? Okay. Now in the literature, there's a very recent model which is rather popular in recent years. It's called degree-corrected block model. It's an extension of the classical block model, which was proposed in the 1970s, and degree-corrected block model is unproposed 5 years, I think. Okay. In the very simple setting, let's start with k equals 2. So we only have 2 community. So the idea here is I'm going to impose a low-rank structure on these, but I also need to take care of the degree heterogeneity. For example, in the co-author network, for example, if a senior researcher, they have a lot of collaborators, so the degree is very high, and for a graduate student with just fresh graduate student just graduated, he probably only have 1 or 2 collaborators. So you have to take care of the degree. Okay. Now the assumption here is after the degrees are removed, then the chance of a pair of collaborators collaborate only depends on the community it belongs to, no longer depends on the degree. Let me give you an example. If there's a statistician and there's a machine learner, okay, so let's take away their degree. So then that model, the degree models how senior, how productive, how likely they collaborate with other people. Then a statistician and a machine learner, their chance after degree removed is only depends on whether you're a statistician, okay, if there's a 2 person, okay, if both a statistician or both are machine learner, their chance only depends on the community. And if one statistician and another is machine learner is a different number here, okay. Okay, here's some, here actually is some kind of old slides from the weblog data, okay, I forgot to change them, okay, so don't be distracted by that, okay. It just makes, okay, I hope this makes sense. So therefore, in other sense, if we use a set I and a set j to model the degree, and then we divide omega ij by these 2 numbers, then the ratio only depends on load I and load j belongs to which community. The no longer depends on the individual node, but only depends on the community it belongs to, okay? So immediately, we are able to write omega as a rank 2 matrix. Theta, capital theta, is the diagonal matrix where the diagonals are the degree parameter we introduced. L is a 2 by 2 block matrix. If we know the label of each of them, if we know the label of each node, we can shuffle them to rearrange this 2 by 2 block matrix. But unfortunately, of course, we do not know. Okay. Now, this is, okay, you write these 3 numbers in 2 by 2 matrix, then this is actually, this matrix can be rewrite as this one, and this is rank 2, okay? This is indicator vector of V of K, seems to be known, but actually it's not, because it only takes value of 0 and 1, but which coordinate is 1 and which coordinate is 0 depends on that load belongs to the first community or the other community. And this is actually the main interest, the quantity of main interest estimate. Okay. Okay, so the generalization to general K community is straightforward. Okay, you just replace P by K by K, symmetrical, non-singular, non-negative, irreducible matrix, and that's all. All other notation is the same. Okay. Okay, so this is proposed by Carroll and Lewman in 2010. The problem about this one is, in the original data set, we have, say, very sparse matrices of 0 and 1. Now, you have introduced n free parameters, which is the degree heterogeneity parameter, okay? So if you have 10 times n ones, that's your number of data points, and you have n parameter to estimate, this is a hard problem, okay? because the estimator would be very noisy and you would not get good results. Okay. So what I'm going to propose today is a new spectral clustering problem which can remove those degree heterogeneity automatically. So therefore, although you have to model the degree heterogeneity so that you have to use n parameters to model them, so that makes the model much more complicated. But it turns out it's a very easy way just to remove those heterogeneity parameters. So as the central surprise is, as far as complete detection concerns, low heterogeneity parameters are largely ancillary and they can remove automatically by using the eigenvectors. So therefore, you introduce n parameters, and they are nuisance parameter anyway, they would not get in your way. Okay? So this makes the problem can be solved very nicely. Okay? I'm going to further explain why. Okay? Let me go back to k equals 2 case again. Okay? In the k equals 2 case, so this is the data. This is omega matrix, let's recall, it's rank 2. Okay? So heuristically, we hope all this other part would not give you a lot of trouble. So therefore, this matrix and this matrix is approximately equal in the sense that maybe the two leading eigenvalues of them are close to each other, or the two leading eigenvectors of them are close to each other. Okay? Of course, these two matrices could not be close to each other in Frobert's norm. Okay, that's for sure. Okay? Now, guided by this heuristic, we can easily calculate the two leading eigenvectors of this matrix, rank 2. So it only have two non-zero eigenvalues. The corresponding eigenvectors is given here. If the plus here is the first one, if the minus, then the second one. Okay? So here are some numbers, A, B, C, D1, D2. These are numbers depends on the degree parameters. Now, the first leading eigenvector can be rewritten as a diagonal matrix capital theta. Remember, this is the diagonal. Times the indicator function of the first community plus a number of the second indicator of the second community. Now, the second eigenvector is very similar. The only difference is this number is different. Okay? Now, therefore, if you give me these two eigenvectors, I divide one by the other entry-wise, or coordinate-wise, then what happens is this matrix will disappear. Okay, right? So therefore, the degree heterogeneity parameter here would not is cancelled, or is almost cancelled. All their influence is in these numbers. Okay. So this is the way how we remove heterogeneity parameter and treat them as ancillary. Okay. So the key observation from the previous explanation follows. In the very simple case, k equals 2, let these two vectors be the leading eigenvectors x. Correspondingly, let these two be the leading eigenvectors omega. We know this one, we do not know this one. Okay. Then we take the entry-wise ratio of these two, we got one vector. We take the entry-wise ratio of these two, get another vector. We hope this vector and this vector is proportional to each other approximately. But the right-hand side is a very simple vector. You can calculate them. It's proportional to a vector of 1 if load belongs to the first community and a different negative number if it belongs to the second community. Therefore, if you cut at 0, if you give you very good community detection. Okay? Because it's positive in one community, it's negative in another community, so you can just threshold at 0. Okay, so general algorithm is very simple. Okay, if you tell me there are k community network, then we obtain the k leading eigenvectors of x. Then we do this trick. Okay, divide the second one by the first one entry-wise, divide the third one by the first one entry-wise, so on and so forth. Then you form a n times k minus 1 matrix. Then you apply k-means. Okay. So any questions? Okay, how does this perform? Let's use the weblog data. The weblog data, if you have done some social network work, then you should be very familiar with this. This is one of the very few network data available where the ground truth is almost given. So the data is collected around 2004. when we have when I think the George Bush's second presidential election. So there's a lot of weblogs online discussing the politics of the United States. We have cleaned the data a little bit, as done in many other literature works. We have these many weblogs, that's loads, and these many hyperlinks, that's edges. For simplicity, we only consider two-side edges. Okay, so it's an undirected network. Okay, so this number is only 13 times n, so it's very sparse, as I said slightly before. Okay, there are two perceivable community, liberal and conservatives. Okay, I'm going to apply the procedure to this one. Okay, remember we have introduced the n by k minus 1 matrix. K equals 2, so that matrix becomes a vector. Okay. Now, what I'm plotting here is 1, 2, 3 up to 1222. So this is the loads. Okay, these are this vector. Okay, because k equals 2, this matrix reduced to vector. Okay. So ideally, if there's low noise, then it's positive for conservative, negative for the liberal, right? There's some noise, but it's pretty clear. Okay, it's pretty clear. If you cut here, it gives a very good community detection. Okay. Okay, so if you threshold is 0, it gives you 82 errors out of 1222. If you use k-means as proposed, you get 58 errors. And if you cheat a little bit, and choose ideal threshold which minimizes error, you cannot get down more. It's on 55. Okay, so basically we have a 58 here. Okay. What? Is the revert one? I think this is red, or this is a conservative, right? Republican. Oh, so, okay. Okay, I'm sorry. Okay, it's the other way around. Okay. So I'm going to. How much time I have? 12 minutes. Okay. So there's other spectral methods like Newman's method and ordinary PCA without this kind of trick, and you can have many others. And there's also long spectral method, especially those by Carl Newman and so on and so forth. I'm going to make it quick here because I have a second section to speak about. Okay, so here's the comparison of errors. The Liu method get a 58. Ordinary PCA, or normalized PCA, pretty bad. Newman spectral is slightly higher by 11 errors, and the profile likelihood method, which is very close to one of the Newman's modulars method. It's unstable. This is a standard deviation. Okay, it's unstable because they need a random starting. Okay. So I'm going to skip this. Okay, let me just summarize the first part by saying I have proposed a simple method which is appropriate for degree block model, and I have exposed the insight why this is a reasoned approach. Okay, because it's simple of the method, so it's easy to use and easy to generalize. So if you have much more complicated in mind, you just feel free, welcome to generalize. And also the other remark is about you can have about DCBM. You can have a more complicated model for sure. Okay, but the simplicity of a degree DCBM also make it ways for generalization and extensions. Okay. Now, there's some theory, consistent theory, and basically says and some regularized conditions. Okay, so this method actually gives you a very tight error bounds without without much models about the degree heterogeneity parameter. Okay, so I would like to use the remaining time to report some preliminary results about some of the other work I've done recently. Okay. Last year, Pengsheng and I have collected 2 data sets based on the statistics papers published 4 of the top journals in statistics, Annals of Statistics, Biometrica, JASA, and GRSB between the time period of 2003 to 2012. So this is a 10-year period. Okay. So we basically collected 2 networks. One is the citation network. This is a coauthor network. So this is undirected. This is directed. Okay. Okay. So plot in the center is a giant component. In all these papers, we have this many authors. Okay. In the citation network, in the giant component is this many. The others are not collected them. It's either not cited by them or not cited those in the giant component. And this is co-author. Okay. Our analysis will be focused on the giant component of each of them. Depends on how much time I have. Okay. So the degree corrected bulk model for direct network is very straightforward. Here, before we have two diagonal matrices. I'm going to allow this diagonal matrix to be different from this one, and I'm also allow this matrix to be not symmetrical. That's only two differences I have compared to before. Okay. Then the score for direct network is straightforward. Okay. You do a singular value decomposition rather than a spectral decomposition. Then net U1 is the first column U, V1 is the first column V, then these are the support of them. Okay? They have coordinates can be exactly 0. Okay? Because it's not symmetrical. Okay? And we construct n times 2k plus 1 matrix as follows. This is column, these are the rows, these are the columns. Okay? The first k minus 1 columns is the same kind of trick. But when the denominator is 0, we do not calculate them. Similar here. For the next k minus 1 columns, we do this or this if the denominator is non-zero. Otherwise, okay, we do this. Okay. Then first of all, we can apply k-means to this part. Okay. Then for nodes in here and here, we assign labels by closest the center of the k clusters. And very few nodes would be in this class. In the citation network, only 14 nodes by doing that. So you can do arbitrary way. For example, you can assign labels by the largest in and out degree. Okay. Now here are the results for the citation network. It's not symmetrical. The scree plot suggests there are three community. Of course, there must be much more than that. But the spectral analysis shows maybe the 3 eigenvalues can be used. Okay. Others are, okay, it's just too close to others. Probably you cannot use them very well. Okay. Now, this is a n by 4 matrix. Remember k equals 3, so this is n by 4. We take the first 2 columns, we take the last 2 columns, because this corresponds to the left matrix of the singular value decomposition. This is correspond to the right. So we plot the second vector, a second column versus first. We plot the fourth column versus the third. Then we do the clustering. Then there's a 3 clustering, and here, okay, 3 different colors. Now the question is, would this be meaningful? They can always give you a cluster, but would they be meaningful? It turns out these and these can be recognized as the high-dimensional variable selection community. These can be large-scale multiple testing community. These are some community we do not know. Maybe it's applied Bayesian. Okay. Now these are the first 2. Okay, these are the first 2, blue and green. This is blue. You see the authors here. Okay, this is Jiashun in the center. Okay, so if you're a statistician, you probably know most of the people here. These are not all the people. We only plot those in the community with a relatively large degree. Probably we just pick like the first 30 or something. Okay, like this is Jiashun. This is okay adaptive lasso. Okay, Jiju. Okay, with adaptive lasso, group lasso, like a SCAD. All these kind of methods authors are shown here. Okay. These are the largest scale multiple testing. Okay, this is Yof Benjamini, the paper by the fourth discovery control person, Larry Wasserman, okay, Crystal Genevieve, and Donald N. Johnston, and Brad Efron. Okay, a lot of them are major players in these communities. Just a joke I'm going to make up is what Stanford Statistics Department has been doing in the past 10 years. Well, you might think it's variable selection. We have 3 professors there, like Emmanuel Candice. There's Robert Tibishwani and Trevor Hasty. Probably you can find it faster than me, okay, somewhere, okay. Trevor's somewhere. Okay, anyway, it's there, okay. 3 stand for statistical faculties are invariable selection here, but 5 of them are here, okay. They are Brad Efron, they are Donahoe, they are Johnstone, they are Joe Romano, and they are David Zygmunt, okay. So this is probably true because when I was a student, that's about 14 years ago there, is every day is talking about force discovery control. Okay, it's a lot of effort of that department devoted to large-scale multiple testing and the force discovery rate, and this is some of the results. Okay. Okay, the third community shows it seems like applied Bayesian, and they have like doing people like Ray Carroll, they're doing like application related to biostatistics or genetic genomics. And a lot of them using Bayesian method. So this one is less structured compared to the first two. Okay. We can also apply it to the co-author network, and they revealed many very interesting communities. The first one is James Berger's objective Bayesian community. If you're a statistician, you must know this one. These are very small group of people. They are tightly co-author with each other. Most of them is James Berger, James Berger's colleague at Duke, James Berger's student and friends. Okay. This is a community about 20%. Okay. And the second one is also applied Bayesian, okay, including part of the people in North Carolina and part of the people in Harvard biostatistics. The third community, the largest one, you might guess, is called high dimensional community. It's so large, so I only report those loads with 15 degrees or more. So you can see most of them, like Peter Hall is the most co-author, okay? It has like 48 co-authors in this 10 years period. Jianqing Fan also has a lot, and think Ray Carroll somewhere here, he has 46 co-authors. So these are the influential loads, okay? More surprisingly, we have many other meaningful communities detected. For example, the theoretical machine learning community. Okay, a lot of people doing machine learning, but in statistics, there's a small group of people who doing machine learning problems, but with a very theoretical, statistical theoretical approach. Okay, they including very visible persons like Alexandra Chibakov, and maybe to outsiders, less visible person, but very, very good statistician, John Waller, and so on and so forth. Okay, these are the several friends and their postdocs. Okay. Actually, okay, like the Bing Yu is also here, okay, at Berkeley, okay, and Peter Billman, okay, so on and so forth, okay. And this Dennis Cook's dimension reduction community here, okay. This is about 18%. Most of the Dennis Cook's student, okay. So most of them are Dennis Cook's student, and he has a student, Francesca, went to Penn State as faculty, then she becomes collaborates her colleague Bing Li, and Bing Li produced another student. So this is more or less this community look like. Okay. Okay, I would like to think my time. So first, I would like to wrap up that I've proposed a score as a fast new spectral approach to community detection. The central surprise is we have to introduce n free parameters to alleviate degree heterogeneity, which seems to be scary because you have very limited data, but you introduce so many free parameters. But surprisingly, these parameters are largely ancillary and can be very conveniently removed by taking entry-wise ratio between the leading eigenvectors, and thus a very nice clustering results. Theory is largely skipped there, but you can go to my website if you want to read more. The proof is highly non-trivial because it leads recent development in random matrix theory. Okay. Some of the key result is only available in 2012. And I also take the time to report some preliminary results in Statistics Citation and co-author late works. So the first paper is out for a long time, so you can download. The second paper, including the data we collected, is going to be made available by the end of the summer. Okay, thanks for the attention.